All right, this is our last bit on the public key technology, and Bitcoin uses elliptical curves, which is just a type of the discrete log problem. And the discrete log problem uses a set of numbers, and it uses these two equations. Log is the inverse of exponentiation, and this allows us to build cryptographic ecosystems. And the elliptical curve is just more of a general type of accomplishing the exact same thing. And we're gonna go over how. And we're gonna show the advantages of why the elliptical curves also came to be. So starting at the beginning, what is an elliptical curve? So just a look at polynomial equations. This is an equation for a circle. This is a special type of polynomial equation is what an elliptical curve is. And just to do a quick example, you see y here is going to be the square root of this value, which makes it positive and negative. So you can see this symmetry over the x-axis. And in the early 1980s, this was the first time that elliptical curves were attempted to be overlapped with cryptography. And then these two individuals went on and furthered the idea and independently co-invented elliptical curves in 1985. The mathematics with elliptical curves are so complex, advanced, and involved that it's very, very hard to make your own curves to use. So a number of groups all over the world, over a period of time, they eventually converged on about 24 curves where all of the information you would need would just be given to you in a standard, and really all you had to do was select a random number, and all the other components, or what would be public knowledge, would just be handed to you. These were curves that had already been through the mathematics to develop them correctly. So how are they used for elliptical curves? So there's three types of one-way problems we're looking at: integer factorization, discrete log problem, and elliptical curve. So right now we need to just ignore the names and focus on what happens in this one-way concept here. So if we know our secret number, it doesn't matter how big this number might be or how many bits, whatever, it's trivial for a computer to go one way to determine, in this case, x. It's very easy for a computer to do that. But if you only know x and that's all you're given, one-way functions force you in a situation to where you have to use brute force to guess and check and try to reverse engineer this secret value. And the number of steps you have to do to guess and check grows exponentially. Elliptical curves do the exact same thing, but they are much stronger, especially when it comes to this piece. So ignore the names for a second. I mean, and also this is what it's called. It's called a generalized type of the discrete log problem. But I think for the next few minutes, if you ignore the names, it becomes a lot easier to understand what's going on. So in the discrete log, we have a group of prime numbers. We have all of these relationships. It results in this random output, this cyclic output. Here our b is 2, our y is 1, 2, 3, and so on. And the results are random. So now we're gonna rearrange the slide now. Discrete logs here, elliptical curves here. And again, these are the conditions you need to have the one-way function, but mathematically there is more going on that now we need to get into in order to understand how elliptical curves compare and really are analogous to the discrete log problem. So first, elliptical curves also use a circle of prime numbers. It's called a finite field from 1 up to p. For the group operation, the math that's going on, for here we had integers and we were using exponents, but really exponents is just a way of multiplying integers over and over again. So now we're not using integers, we're using points on a curve, although each point is also an integer, and each integer is going to be within this prime field. But the math that we're doing now, the math that we have to do, is not multiplication, but it has to do with math with points on a curve. And then each of the points that we yield are going to exist on this curve, and we're going to use this small example curve. It's popular for elliptical curve examples. And there's also a base generator. So here we had this number that gave us some special properties. And it's the same thing with elliptical curves, as we have a number and then along with some other conditions are what's going to end up giving us all the properties we're looking for in a cryptographic ecosystem. So now back to the actual math that we're doing. The math operation that goes on with curves is called the tangent and chord method. And this is a common method. It's how you find a point on a curve if you know 2 points. So bear with me for a second. It's a two-step process here to do the tangent and chord. So step one, you take your base point P and you have to double it. So just go with this for a second. We're at point P. We're going to make a tangent line and extend that line until it intersects with the curve again. Once it intersects, we mirror the intersection, and that's our answer. That's the tangent and chord method on what's going on. And for step two, we're going to add P. So what we're doing is we're taking this P plus P and we're adding the original point P. And again, we're going to connect these 2 points. This is now where they intersect on the curve. So we mirror from that, and this is what gives us our answer of 3P. So we have math equations that govern this. These are the equations that the computer is actually doing when it's going through elliptical curves. And you can think of S here as this is how you would derive your X and your Y, and the S is the curve. You can think of S as the curve, and these are the values of S for step one and step two. And in the format of this equation, in our example here, this is where the value A comes from. So now we're going to walk through. So now we're going to walk through this example. We have mod 17. We have this curve. This is our base generator. And first we need to do step one, double the base generator point P1. This is, we touched on this briefly a few videos ago, but when you divide in group operations, it's not the division we think about. We learned in elementary school. You're actually doing the inverse. There's a process you go through to find the inverse. So these steps are not necessarily straightforward to follow, but for now, just know that the answer to S for this is 13. And once you know your S of 13, you plug it into your equations and you get your new X value, your new Y value. This is your P plus P. This is your point. This is 6,3. So you just did a bunch of math and you arrived at a point 6,3. So now we go to step two. We're going to take 6,3 and we're going to add P. So we're going to add 5,1 and 6,3 to get 3P. So here S is a little more straightforward. Our answer to S is 2. And go through the math on that, and we get our next point, 3P, of 10 and 6. So now we're going to repeat step two. We're going to add our 2 points, 6,3 and 10,6. 6,3, 10,6. We solve S. We solve for the new X and Y, and this is the answer we get if we were to do all that. Our answer is 3 of 1. And then we add 10,6. We keep repeating this second step. We keep adding P, and we're going to do it to fill out the rest of this table. So okay, we're going to pause here for a second and rearrange the slide. So here let's recap some similarities we're looking at. So both. We're using a finite field as the string of numbers. We both have these modular arithmetic processes where the results we get from that, whatever operation we're doing, the results are going to be inside of this ring. Both of them have, both elliptical curve and discrete log had this base generator, which gives us some special properties. And for elliptical curves, our base generator is going to generate this group up to 18P. And then we arrive at this. This is our X value is repeating. Then we have something we're going to talk about next, and then we start over the cyclic group again. So the takeaway point, though, is that the elliptical curve has all the same ingredients as our discrete log problem, and to include the cyclic nature of this group. And we'll talk this briefly, but this is kind of a mathematical hand wave that's done when these curves are created. This is an artificial point. It's called the point of infinity. And the point is this: when you arrive at a certain point on your curve, if you were to take this line and just bring it up as far as you can towards infinity, at some point it doesn't matter if you're off by the left or to the right a little bit. At some point, if you go up high enough, this curve just runs perpendicular, and this allows you to use your math operation, and to the result is you're going to go back to the base generator. So this box here, it's known as the point of infinity, but it allows the math to bring you back to your base generator point. And again, it's kind of a mathematical hand wave, but it ensures that we're going to have all the properties that we need in this group. And then this sequence of points here is cyclic. So once you start over at 20, this sequence of points is going to continue to repeat itself. And then just one last similarity to point out is if you start mapping the results on a graph, because here's point 1, here's point 2, point 3 jumps over here, point 4 jumps back here, 5 is way up here. You can see there's this random nature of where these points are landing on the curve. And at this point, you can't really see an elliptic curve. Elliptical curves aren't going to materialize when you do this, but you still can see that there's some symmetry going on, and it's the modular nature of the arithmetic is what's breaking them up and kind of spreading them all over the place, and also kind of ruining the nice geometric elliptical curve we were able to see earlier. So now we're going to take this all the way back to our starting point, and we have B, which is a point on the curve. It's also some point that's going to generate all other points. Roughly, the number of points is going to roughly equal your prime number, but not exactly, not with elliptical curves. X is also a point, and Y is an integer. It's the number of times we perform the group operation, and the group operation is performed in modular P. So if we are given B, Y, and P, it's trivial to compute X. And also Y is always going to be less than P. It's minimal steps for a computer to do this. And we're not going to get into how the computer goes through this equation. It's called binary scale multiplication, but it's actually the exact same process between elliptical curves and the discrete log problem in our last video. It's the same process that's used. But now, elliptical curves, if we are given the inverse problem, we're given B, P, and X, and we're asked to determine Y, the number of calculations we've done, the number of hops around the curve, it is exponentially infeasible to determine this. And we can do guessing and checking. Computers have a little more advanced algorithms in order to let them move this faster, but computers still, the number of operations they have to do is going to increase exponentially as we start adding bits, number of bits to our equation here. And let's compare this right now to the discrete log problem. So with the discrete log problem, the number of steps you need for brute force are much less, P over 2 compared to just P. So what this translates to is that elliptical curves are about 5 to 10 times lighter and more efficient and faster for computers to perform these cryptographic operations on. So now what we have again are all the right conditions for a one-way function and the conditions for a cryptographic protocol. So in the elliptical curve one-way function is used. It's very similar to how we used the DLP in the protocol we covered recently. So here's what it looks like. Is Alice and Bob both select a random number between 1 and P. Alice and Bob both compute their public key based on this secret number they have. They're going to exchange public keys. Alice takes Bob's public key, here it is, X of Bob, Y of Bob, multiplies it by her secret number, and she gets a secret key, K of AB. Likewise, Bob does the same thing. He takes Alice, x of Alice, y of Alex, times his secret number, and they end up again with the same point. It's a way for them to arrive to a same secret number. And a good way to view this is with our earlier example, and we'll walk through this. This is the elliptical curve equation and the base point. Alice picks 3, Bob picks 9. So they each pick a secret number, and now we're going to reference our table. Alice starts with 5, 1. Now she goes to 3p, which is 10, 6. Bob starts with 5, 1, and he goes to 9p, which is 7, 6. Alice and Bob exchange these publicly and widely known points. They exchange them. And then let's look at this last part here of why they arrive at the same number. So Bob is starting at Alice's point, and he's moving forward his secret. Alice is starting at Bob's point, and she's moving forward her secret. And you can see that's why they end up at the exact same point. The point they end up at is 1310, and it is a secret point. And now, just like with DLP, they can use the coordinates. A lot of times you just use the x coordinate, and you use that as your secret key to perform the DES operation, and you can exchange a very long message. So in conclusion, the elliptical curve equation here is just a one-way function. It can be used to build the cryptographic public key ecosystems, and it solves the key distribution problem.